to boiling point elevation, and the boiling point of a solution is higher than the boiling point of the pure solvent. Our picture of this is we've got a solution, and inside that solution there are solvent molecules, but then there are also solute particles, if there's any ink left in there. Solute particles, and as the solvent particles have enough energy to go towards the surface from wherever they are in solution, they bump into the solute particles. And here, let me write solvent particle. And so, of course, there are so many more of these. I'll only draw a few. But as they try and go to the top, they bump into a solute particle. The solute particle effectively blocks or takes some of the energy that they had, slows down the solvent particle, and makes it so that you need more energy than you would normally for a liquid to boil. The form of the boiling point elevation equation is exactly the same as the form of the freezing point depression equation, except now we have two B's in here. The change in the temperature of boiling equals the Van't Hoff I factor times molality times the boiling point elevation constant, which for water, 0.512 degrees per molality. And I, so I equals the Van't Hoff factor again. Now let's take a qualitative approach to this. So for this one, which of the following has the highest boiling point? And you can see we've got different types of solutions, and we've got different molalities here. So let's see. So I'm going to go ahead and put I here for the Van't Hoff factor, and then I'm going to put I times M, because for the same solvents we will have the same Kb. So if we're looking at different solutions, we have to look at the I times M to make the difference. Sodium chloride, we've already talked about how it breaks into two particles, I equals 2, C6H12O6. If you recognize this as glucose, or one formula could be glucose, and glucose is a non-electrolyte, great. Otherwise, carbons, hydrogens, and oxygens, unless it has the COOH group. If it doesn't, it's a non-electrolyte. I equals 1. Aluminum nitrate, ionic compound, has 4 ions in it, 4 particles. Carbon dioxide, that is a molecule. Again, it only has carbon, oxygen, not even hydrogen. I factor of 1. And ammonium chloride only has 2 ions in it, Van't Hoff factor of 2. So multiplying these together, 0.10, and this is going to be, yeah, we won't have units on that. I guess it could be, it is molality of particles. Molality of particles, 0.05, 0.08, 0.005, and 0.04. So your strong electrolyte with your more, oh, is that right? Yeah, okay, good. Sorry, I had to think about it for a second there. Your sodium chloride has the largest concentration of particles and would therefore have the highest boiling point. And of course, it's not a perfect world. You can see that we have what we would just figure out. Even for iron chloride, we expect that I will be 4. We measure them, or if somebody measured them, it wasn't me, you can see that it's not perfect. That's due to ion pairing. Of course, these ions are attracted to each other. And the only thing I want to show you here, well, two things. First off, if you get a problem on the homework, use the expected values, unless it says otherwise, and I don't think that will happen. But then just know that the ions are attracted to each other, even though they've got their hydration shells around them, and that in general, as the ionic charges get bigger, the measured values for I get farther from ideal. We can see 2 is 1.9 for sodium chloride, and then plus 2 minus 2, we get all the way down to 1.3. Anyway, we'll use the ideal or expected I values.